And let's see, I did make the slides that Linda's going to be throwing up there. So I guess I'm just going to start, okay? And I'm starting with this just because, oh, there's Linda with the slides. Wow, that's great. Thank you, Linda. Linda, skip this slide, go to the next one. That just says what date it is. I know that. Okay, great. Okay, so I'm just talking with you, but you should realize that down here, and let's see, they maybe can't see me, so I'm going to do this little pointy thing. Now you should be able to see my, this little finger thing, the index finger. So I'm just going to talk a bit, but there is an opportunity where I'm specifically going to ask you, or your questions and answers and stuff like that. That will happen, and we're going to conclude with our poll, Linda, about just how are people and things like that. And Linda, you have a little slot here, but I go first. Okay. First of all, you should know that we're approaching the 12th week of the term, and I do know what time it is. It's 6:02, and I also know what time it is during the term. So I'm saying approaching the 12th week. Next week is the 12th week. Now, I'm happy to report that we are on time and on schedule. It hasn't really been easy on anybody, but that's where we are. So that's good news, okay? We're on track for arriving where we need to at the end. So that's good stuff. I do tell you, though, that keep your seatbelts fastened because there's all kinds of turbulence out there. I know about that. And I'm really excited looking forward because tonight we're pretty much going to be finished with Chapter 4. That means we'll be moving into Chapter 5 in the textbook. But what will happen is we'll finish up the physics stuff and we'll conclude by doing a lot of really straight up ultrasound stuff, which is really perhaps my favorite part of the course. Okay, now so that's that part of the story. So far, so good. Values. I like to remind students of my values, and that sets a little bit of a context. And I know you've listened to this before, but I'm telling you again. My number one goal is to provide you the best content course possible. And the reason that's my goal is because I can do this, and I can kind of guarantee that I will do the best I can, and that will be a very good course. Okay, and I'm constantly thinking about that. In fact, Linda and I were working on some video possibilities that could have made the course even richer, and those may or may not work. But anyway, that's in my mind a lot. That's my number one thing. Okay. Now, my number two thing is I want to manage student anxiety. That means I don't want you to be anxious. I want you to say, no, I'm trusting, the course you're giving us, and that you're available for us, and so on and so forth. And I am. For example, on election day, what I did is I was watching the returns on, let's see, I guess I can tell you what channel I was watching. Is CNN. That's where I was watching. But I would turn us off because I did come to class that night, even though I wasn't supposed to. That's what the college said, but I said, no, I want to be there for my students. I did both my office hours that day too. Now, no one was hurt, and those weren't mandatory, so that's all good. But I do want to do everything I can to manage student anxiety. You might say, well, Jim, why isn't that number one? Well, that's number one because I have some students, and this is true, I'm not telling you who they are. I have some students who are living in their cars. And that is an unfortunate situation. And I'm glad that we've had a little bit warmer weather lately, just so they're not so cold and things like that. But there's a lot of anxiety out there, and I can only manage some of it relative to this course. But I want to manage what I can relative to this course. My third thing is I want to render grades so that you guys can accomplish what you need to and move on with your lives. And in this process, however, though, consistent with the top two, beyond a wholesome discipline. Now, if nobody does a lick of work the entire term, doesn't take the midterm and doesn't take the final, they're not going to get a good grade because that's just disciplines that's expected. But this is a pretty gentle process. I do appreciate the challenges people are living with and through, and I applaud you for that. And so I'm not trying to be harsh here at all, okay? And just kind of in summary on this whole thing, I think you all are okay. And I encourage you to view the final exam as an upside opportunity. And we're entering, I don't know if I'd call this the home stretch, but in track, they would call this the bell lap, meaning this is the last big lap that we're taking, is the one that we're on. So you're all okay so far? This is an upside opportunity. Finish strong, and I think you'll be fine. One of the things that Linda and I are going to be doing is showing you a copy of the LSI 11 or LSA 11. Now, if you were able to watch the videos, and I certainly make the videos, I actually spend a lot of time making those videos and constructing those videos. Some of you might have seen this already, but we're going to look at it just briefly during the thing tonight, so it's going to be on another video. And I'm going to maybe ask Linda to post this and do things like that. And Linda and I are, well, we're discussing this just now, and maybe I'll double check with her. In fact, Linda, you still there?
I got it. I'll take care
Okay,
of that
so good.
probably tomorrow.
Okay, so anyway, she's going to be sticking this out there for you and things like that. You'll see it tonight if you're watching along. And I think I said it was due 11/12, and that's 1 week from tonight, and that's good. I'm giving you these low stakes assessments so I can say, no, look, I had them do some work. And these are opportunities for you to learn. So, these are good things, but they're low stakes. That means that nobody's getting screwed with their grades for these. But it's an opportunity for you to learn. And I work with many students in my morning and evening hours, and I'm assuming that people are visiting Linda and Tom Topol and, other sorts of supports that I have for you. So anyway, we'll talk about LSA 11 just a little bit tonight. And then this is an important topic that I want to mention quickly. I was happy to do accommodations for students because I believe that students certainly should be accommodated, and during the COVID period, certainly for that. But here's what happened. The midterm happened in the middle of the term, so there was a lot of, opportunity for things to happen after the midterm. We do not have that luxury at the final exam. So I'm going to be starting talking about the final exam, saying, hey, this is the date and this is the time, and these are some of the broad parameters. I'll be talking about that along the way, but I want to know about your accommodations early rather than late, because you see, when the final exam happens, Jim is going to be grabbing those papers, grading them, and giving students final grades. And so there's not going to be a whole lot of room after this for you to say, oh yeah, I wasn't able to show up, or I didn't show up, or I chose not to show up, but gee, give me a makeup. Well, and I don't know if disaster happens, I'll certainly listen to you and try to help you. I do want to accommodate you, but for Pete's sakes, let's do that ahead of the final exam rather than after the final exam, because Jim's going to be turning in grades then. Okay, and the dates. Actually, I think I've already given you the dates, but I'll give them to you again. The times will be announced soon. Now, we are constrained a bit by the college because the VCM class has to have their exam from 6 to beginning at 6 on the assigned day during the final exam period, because that's the way the college is doing it. And so I'm going to try to have the other one on the same day. And I can't give them a different exam, so it's going to be an hour and 15 minutes long, and so I'm going to be picking and choosing my problems carefully, and more about that. But okay, so accommodations, I'm looking for you to, when I start telling you about dates and times, you say, oh yes, I put that on my calendar. You say, oh my gosh, I can't be there. You talk to me early, okay, and we'll square away something. It'll all work. And someone's asking questions about the final. Question that was asked, and I mean, it's fine, but I'm going to say much more about this later, not tonight. But I expect, you see, if there's 75 minutes, there's only so many questions I can ask. And someone asked, is there going to be 10 questions? If I had to guess tonight, I'd say yes, there might be 10 or there might be 12. But again, it's not going to be 100 or anything. So anyway, this is coming up, and we'll have a lot more to say about that later. Okay. Now, some other comments, because some people have been sending me notes and things like that, and I do read the notes. I try to respond sometimes I respond globally. I say, hey, a student asked about this, and here's a story about that. But then I have meetings and stuff like that. So anyway, here's some comments that I think I want to share with all of you. Some of you might be saying, hey, I think this is hard. It's not easy. And I know that, okay? And don't expect it to be, because I'm teaching you what I'm supposed to be teaching you. So it's not easy. I'm also going to tell you that anything in life that's worthwhile, none of it is easy. Okay. And this is just my opinion. I really didn't review this with Linda, but this is my opinion. But someone did suggest this, and Linda and I gave it a try in this environment. And we actually do this a lot when Linda and I teach the class in a classroom, because everybody's got a workstation in front of them, and we'll break you into groups, and Linda and I will walk around and we'll give you problems to work and everything like that. And in the classroom, I think that works really, really well. And I was uncertain how well it would work in this environment. And I got to tell you that me looking back on it, I thought that was not a good use of our time. Okay, my time, Linda's time, or your time. And it really wasn't anybody's fault. It's just that, when we broke into groups and something like that, one student, for example, communicated with me and said, well, what you should do is put, in each room, put a really good, strong student. Well, that's a lot of work and a lot of arrangement, and I think that's actually kind of hard to do in this environment. Now, it was easy to break people into groups, but then we had media problems and stuff like that. So I was more than willing to try this. I love getting the suggestion. I don't think it worked well enough to do it again, but we'll try things and keep doing it. There was a suggestion that a student made, and this student was saying some things, and I take these things seriously. I said, yeah, this is hard for me, and my response to that is, it's not easy. And one of the things they ask it is, gee, could we have some more sample problems for the final? Well, I'll tell you what Linda and I are going to do. And Linda and I will be giving Linda a copy of the draft content for the final. And Linda is a student, and Linda's very good at this. She'll figure out something that makes sense for you. It may be a topical review, or it may be some problems and stuff like that. But I am going to tell you that, yes, that is what the LSAs are for. And a lot of times there are leftovers. In fact, I'm watching the clock right now. I always know what time it is, and it's approaching 6:15. But there probably will be leftovers tonight. And when I'm talking about leftovers, there's not food, because when I eat, there are never leftovers of food. But I will tell you, I don't think we'll cover everything tonight. Well, that means you ought to look at some of these problems that are in this presentation, and there's some other problems for you to try. And in fact, I include answers there. That doesn't mean Linda and I aren't going to conjure up some final problems for you to practice on and stuff like that, because we want you to be successful. And Jessica, I'm going to ask Linda to speak to that in just a moment, okay? And that's what I'm talking about. And in fact, I'm speaking to it right now, so Linda doesn't have to. There will be guidance for the final. Now, I don't know if the student that asked that will say, well, gee, in high school they gave us a different kind. Well, I don't know, but we are going to give you something, and I'm on your side, okay, up here. So there'll be something, but also you've got a lot, the LSAs, the leftovers, and things like that. But Linda and I will be discussing that. We haven't really yet. Okay, I think I'm finished with that. Linda, this is your slot for anything you maybe want to say. And Linda may say no comment, or I have nothing, but I don't know. This is her slot. So go ahead, Linda.
So just as a quick reminder to everyone, then I'm absolutely happy to answer any emails that you send me. But if you are going to ask your questions via email, then I'd appreciate if you're as specific as possible. Just because if you email me only saying I need help or I'm confused, then now we're stuck playing 20 questions while we try to figure out what the actual problem is. So just, if you're going to send an email to ask a question, try to be specific. If you can't be specific, then going to one of the live tutoring sessions or going to Professor Bradley's office hours is probably an easier approach. That way we can actually talk with you and try to figure out where the issue is.
And included in that mix is Tom Topol. I mean, he has a major in physics, and he's getting a PhD in science and theology or something, which is, that's like really interesting to me. Anything else, Linda?
No, that is it.
All right, great. And Sydney, Sydney, I'm recognizing you, but this is your part of the agenda, okay? This is questions and answers from, the student body, and Sydney had her hand up. So Sydney, I'm calling on you, and so go ahead and ask your question, and Linda and I will give it a go answering. Go ahead.
I had a question. Honestly, I don't know if you guys can answer it, or if someone in the class can answer it. On what platform does Tom Topol do his Saturday tutoring on? Do you know?
Well, I'm guessing, and I'm going to try to make a note here. I'm seriously guessing, and by the way, this is a little bit of guess, but I'm guessing it is either Zoom or it might be Google Hangouts. Okay. Now, and the reason I am guessing that is some of the I have DVAs for other classes, and I know these people actually very well. And some of them I know do the things on Zoom, but others use Google Hangouts. And I'm making a note here, Sydney. I'm going to ask Tom Topol to maybe send you guys an email or something like that. Maybe reminding you of when his things are, and maybe speaking to the platform issue too. So I don't, some students I know have met with Tom, and maybe there's someone in this classroom right now who's done it. But I mean, I'm almost 100% sure it's one or the other. It's either Zoom or it's Google Hangouts. And I know in the Learning Commons they use Google Hangouts a lot, but there's Zoom too. So I will check with Tom Topol unless there's anybody else out there that has anything they want to say. No one's jumping in, so we'll pretend that that's good. Sydney, that's the best answer I got now, but I'll interact with Tom. Anybody else?
Thank you.
You're welcome. Anybody else? Linda knows I like to count, and I counted to 5. Now, that doesn't mean you can't ask questions. If you have questions, certainly ask them as we're going through, but that's the end of at least this line item in the presentation. Okay, so Linda, can you toss up a poll, please? This is just how you doing kind of poll. Okay, so please weigh in. I do care how you're doing. Well, let's see. I think we've maybe almost run out of the response. And Linda, I think 2 of these people are you and me, maybe.
Yeah.
I don't know how you did that, but anyway. So most people responded, and there was a lot of okays. There was a couple of greats. I'm happy for the greats. Actually, I'm happy for the okays because these are not easy times. I think there were 3 or 4 people who said that they were struggling, and my advice to people who are struggling is, I know it's hard. I know COVID's hard and things like that, but do your very best to engage in the things that we have arranged for you. And I got to tell you that I many times do things outside of even those hours if somebody really is having need, and I reach things like that. So reach out if you're struggling, or engage if you're struggling, and that's the best that we can do. Okay, all right. So now we're going to start doing some work. So Linda, go ahead to the next slide, if you will. This is the low stakes assessment number 11. I'm going to read this. The longest home run, according to the Guinness Book of World Records. Guinness is a brewery. We won't go into much there, but they publish a Book of World Records. The longest, actually, Guinness is a very old, famous Irish brewery. It's one of the oldest in the world. Anyway, according to their Book of World Records, the longest home run ever measured was hit by this guy, Dizzy Carlisle, in a minor league game. The ball traveled 188 meters. They changed that also into feet, 618 feet before landing on the ground outside the ballpark. And here's your questions. Assuming the ball's initial velocity was 45 degrees above the horizontal, and ignoring air resistance, which makes the problem much easier than it would be otherwise, what did the initial speed of the ball need to be to produce such a home run if the ball was hit at a point that is 0.9 meters, which is about 3 feet? That means it was in the strike zone above the ground level. Assume that the ground was perfectly flat. And part B is, how far would the ball be above a fence, 3 meters, 10 feet in height, if the fence were 116 meters, 380 feet from home plate? So you see, you got a bunch of different units here. You got meters and feet, things like that. And this is similar to a problem that we worked on before. It's a little bit different because the problem that we worked in class last time, or in the video, I think, I don't know if it was in class last time or in the video, but anyway, the ball was on the ground, basically. We didn't say it was in the strike zone. So you see this part right here. I think I'm going to find Linda's pencil here. This part here makes this problem look, now that it didn't give me the pencil. Maybe it did. It did. That part there is a little bit different than what's in the video. But we'll talk about that. You got time to do this. These are take-home protocols. This is a low-stakes assessment. So working with Linda or working with me or, you know, so on and so forth, Tom Topol, that's all good stuff. And you can do this. And Linda's going to guarantee that this gets, well, Linda is going to grace me by posting this in there, but you can see it right here. And, you know, so it's there, and she'll arrange places for you to put it and stuff like that. Okay, so that's going to be due in a bit. And we'll probably have an assessment 12 and, you know, so on and so forth as we go forward. Because I think these things are good for you in many respects. And this is an example of projectile motion, and we're going to open tonight talking a little bit about projectile motion. Okay, so Linda, go advance the slide. Okay, now, one of the biggest things about projectile motion, well, actually, there's two things. I talked about both of these things in the video. In fact, I even show you some strobe figures, camera shots, things like that, where you have this. But the important thing is that, let's see. I'm not sure if I can do this, but I'm going to try. And it looks like this happens, so I'm just going to add this. This is an important thing. Horizontal and vertical trajectories are independent. I actually show you why this is true, or at least I give you some experimental experiment. I show you some pictures and stuff in the video as to why this is true. But this is really a big deal. See, now this is projectile motion, so what that means is when this baseball is hit, it's hit with initial velocity, but that's a vector. This is an angle, so there's a launch angle and things like this. And what you do whenever you have a vector like that is you can break it into the initial velocity going in the x direction and the initial velocity in the y direction. But what I just told you, again, I told you once in the video, and I'm telling you again tonight, the horizontal and vertical trajectories are independent. Now, that's kind of an amazing thing. And that's something that students kind of have to be told, and I've told you twice now. But that means you're going to solve this problem two different ways to answer the questions. One thing is the up and down happens in the y direction, happens differently than along the x. And I think it was 9 was going along the x-axis, and 10, let's say 10 was going up and down, and now we got a problem where you have to do both of them. So the horizontal and vertical trajectories are independent. But what we have is we have all the equations that we need already. So here's this then, and this is set up for projectile motion. These will be useful equations. And actually, there's one equation that we're going to use that's not listed here. What really happens is you solve for t. Let's see. You can solve for t and substitute in. I'll show you that equation again too. But basically, you see the velocity in the x direction is just the initial velocity in the x direction. So you see, when you find the component of the velocity at which this guy hit in this direction, it just keeps on going that speed all the time in the x direction until it hits the ground. So you see, that's an important thing there. And also, how far it goes is x is equal to x0. And again, you got to think about where that one actually started, because it didn't start at 0, 0. But x is equal to the place you started plus velocity times the time. So you see, these two equations are going to enable you to figure out where that hits once you know the time. But y is different, and the reason y is different, you see there was no acceleration here. Velocity was constant. But there is an acceleration that's happening here, up and down, and the acceleration that's happening up and down is gravity. So you see, the velocity in the y direction is going to be the initial velocity in the y direction minus g. That's that 9.8 number that we keep talking about, times t. Okay, so there is an acceleration, and actually that's what makes this thing go up and then come down, because for a while it'll go up, but then it will stop, basically, and it'll start coming down. And you've seen that in some of the other low stakes assessment, and you'll see it again here. Now, the net of all that is, you see the x will be going along here, and the y will be going up here. And actually, this is often this is the x is a function of t as well. But anyway, I think what you see is, yeah, so this is going along just fine. This is going up and then going down. So you see the net effect, since you've got stuff going on in both x and y, is a parabola. It opens downward, and so you have a crust here, things like that. So there was one of the equations in the y direction. This other one is another equation in the y direction, and this was y is equal to y naught plus v0t minus 1/2 gt squared. Okay, so anyway, all these equations that we learned before apply, but you've got to remember that horizontal and vertical trajectories are independent. Linda, let's see the next slide, please. Okay, now this is really a good problem for us to study, and we will go through the solution, and we'll do other solutions as well. And again, the problem I ask you is not exactly like this problem, but it's a lot like this problem. So if you understand this one, you're in pretty good shape to tackle the other one. Again, Linda's available, Tom Topple's available, I'm available, Cheryl Martin's got dozens of people that work in the Learning Commons who can help you with this. Anyway, here we go. I'm just reading. So a test rocket is launched by accelerating along a 200-meter incline at 1.25 meters per second squared, starting from rest at point A. Now, let's decode what all this stuff was. Well, you have a rocket, and you might want to think about this as being a rocket car. It's one of those things that, like, you guys are too young to know. Once there was a daredevil named Evel Knievel, and he would, set land speed records, stuff like that. There's people who do this for fun. And Evel Knievel also would try to jump over things like the Grand Canyon and stuff. And he broke a lot of ribs doing that. I actually think he never killed himself doing that, but he had all kinds of broken bones. Anyway, this is kind of the thing. So you're starting here with your rocket thing, and it's being launched. But you're launching it by having it run along here. Okay, so you fire up the engine, and it goes up here, and then it's launched into the air. Now, so there's different things going along at different places. And you know two things from the problem. This is 35 degrees, and that is 200 meters. And you also know this, and when you see this as meters per second squared, you say, oh, that is acceleration. Okay, so that's what's going to happen. And it's starting from rest here. You fire the engine, and then it zooms up here. So it's starting from rest, and it's going up here. Now, the incline is 35 degrees. And notice that we're launching it at this angle. So you see you've got a vector going there, but you know the angle is 35 degrees, and it goes up here. Now, more information then. At the instant the rocket leaves it, and it here refers to the inclined plane. So at the instant the rocket leaves it, its engines turn off. And so you see it's really subject to free fall. Now it's still going at this velocity, and it'll have an upward component and a this way component, which means it's good. We're practicing that. But the engine is turned off. So the only place where the acceleration happens is on this 200 meters. So it's subject to gravity, and they're saying we can ignore air resistance. If you're really interested in this air resistance problem, I teach differential equations. In fact, I think Linda took differential equations with me at once upon a time, and you know, we study what happens there. But anyway, here's what you're supposed to find. A, the maximum height above the ground that the rocket reaches. So you see this thing goes up and it goes like that, and it eventually reaches, you know, a crest, and it comes down and it hits the ground. Okay, so find the maximum height above the ground the rocket reaches, and part B is the greatest horizontal range of the rocket beyond point A. Now, you do want to think about that, because he said beyond point A. So you see this thing zooms up here, it takes off, does that, lands out here, but they said the distance from here all the way back to A. So those are the questions that we have. And we're going to look at a solution to this now. And so Linda, would you advance the slide, please? Okay. Now, this is important for the leftovers, because sometimes there are leftovers, and I am sure there will be leftovers tonight. So there are problems and there are solutions that you can read. Now, sometimes, and I don't know if this ever happens with Linda, in fact, I will ask Linda in a minute if that ever happens to her, but I will tell you that sometimes students will come to me in the Learning Commons. Back when I was in the Learning Commons a lot, I used to hang out there a lot because I like the people and I like the students. They would come in and they say, you know, I have a solution here, but I don't understand the solution. Well, that didn't mean they were dumb. That means that whoever wrote the solutions probably was doing something kind of fancy and they didn't know how to do it. And I was happy to help them understand it. But this is a solution that was written up by a physics person. Okay. And so these leftovers will have the solutions there, and you should try to read them. Now, I don't care if you come to my office hours or someplace and say, yeah, I don't understand, maybe it's this step or something. You say, I don't understand that step. That's okay. And Linda, I'm going to ask you, do you ever have that experience?
Oh, constantly.
Okay. And do you tell them, do you tell the students that they are SOL, or do you help them?
Normally, I help them.
Yes, I believe that, because Linda is a good person. So anyway, but it's hard work reading these and stuff like that. And it's hard because the subject matter is hard, and I'm teaching you what I'm supposed to be teaching you. I'm teaching the best course I know how to. Okay, so here we go. Now, these solutions that I'm providing often have a setup. Now, some of this stuff I've already talked about. I'm just going to read it with you, okay? Once the rocket leaves the incline, it's into projectile motion. I told you that because we turned off the engine then. The only acceleration then is gravity, okay? The acceleration along the inclined plane determines the initial velocity. This means that initial velocity means the initial velocity when it jumps off the ramp, when the projectile motion starts, and the initial position for the projectile motion, okay? All right, so we're going to talk a bit about this then. Okay, so for the motion along the incline, we're going to call that direction X. Now, that means that and Linda, I don't know how this is going to work, and I don't really know what will happen, but it will be fine. Actually, the thing I don't know what will happen is, in fact, I've scared myself enough. We're not going to do this. I think if we went back to the other slide, it would erase the recording of the audio. I'm not sure how that works, so we're not going to do that. Okay, I'm just going to sketch here, and I think I can sketch. Okay. Okay, so you see they're talking about the motion along the incline. So they're calling that X right now. You might say, oh, you should call it something else. Well, maybe they should, but they're calling it X here. So that's fine. And then no one told you the time. They told you a whole bunch of things. In fact, that's why we're using this equation right here, because no one told us the time. No one told us how long it was on there, but it told us everything else, okay? So for example, we know that the initial velocity is v sub 0 in the x direction, and it started at rest. That's going to be a 0. Okay, so that's going to be a 0. And the acceleration, they told us what the acceleration was. You might remember that the acceleration was 1.25 meters per second squared. If you look back, you'll see that that was it. And x minus x0, that's how long was this thing, and that's the 200. And there's a 2 here in the formula. Now, I told you when we went over this, you might say, I don't remember you telling us that, Jim. Well, it might be you haven't watched the video yet, but I told you in the video that the reason that this equation is so useful is that there's no time in it. So if you say, well, I don't know time, well, you say, maybe I can use this equation. Again, we're on the grace notes, we're going to give you all these equations and everything else, but there's that equation, and that's one of the equations that we studied. We're studying it along there. Okay, so you see the only thing that you don't know here is v sub x. So you can solve for v sub x because you know everything else. So you plug in all those numbers, and you have to take a square root because this was v sub x whole squared, and you get this business, and you plug that into a calculator, and you get that. Now that tells you at the end of this inclined plane, that's the initial velocity, and it goes into free fall or projectile motion. Okay, now that's what they're saying here. When the projectile motion begins, the rocket has, this is an initial velocity, and the angle is 35 degrees. Okay, so that's 35 degrees still down here. And it's at a vertical height of, wow, well, we need to figure out what that vertical height is. Well, you see, that was 200. And that was a right triangle because it was an inclined plane. And so to figure out what the vertical height was when it went off there, I'm going to call that, let me make sure what they called it. They called it y. Maybe they didn't. I'm going to call it y anyway. Okay, so y over 200 is sine of 35, and that means that the vertical height was 200 hypotenuse times the sine of 35 degrees, or 114.7 meters. Okay, so you see, we know we can put, so we know the initial velocity, and we also know we can put 114.7 here, and that is meters. And I hope everybody sees where we're going to, where we got that. In fact, I'm going to pause right now. I'm going to do one more thing, and then I'm going to pause and see if there's questions, Linda. Okay. And maybe I don't know. Let's see. Okay. Now you don't know this yet, but it is going to be important for us to know this distance, because you see, when this thing lands out here, we want to know the distance from A. So we got to know what this distance is. That's going to be, I could call it x, and then x over 200 is going to be the cosine of 35, and that means x is, and that might be a long way before we actually do this. Well, down here we're doing this because let's see. Yeah, Linda's polling or something, so that's good. I'm going to close that for a minute. Linda, you can still see it even though I closed it here, right?
Yeah.
Good. Okay, great. Later on, we need to know that, and so I'm just going to say that x over 200 is going to be equal to the cosine. So we can figure that out, and later on we have to do that. So, and whenever we get to that point, I'll just say, oh, there it is. Okay, but I am pausing now, and Linda's question is a good one. So, okay. So
if you guys do have questions and you don't want to voice them for everyone, you can send me a private message and I can say it for you.
okay, and I'm just going to, someone put a thing there and they said, why did you take the square root? That wasn't what they said, but that's the essence of the question. And yes, and they said, was it because of this? And certainly it was, because you see, I knew all these numbers, so I plugged them in. So to find Vx, which is what I need to know, you do need to take the square root. And yes, that is why I took the square root. And then you say, oh, well, yeah, you mean we have to know the trig? Well, yes, we studied that before. We'll study it again. It's all over the place here. Okay, I count to 5. I like to count, but I get tired of counting. Now, that doesn't mean you can't ask questions and stuff, that, you know, ask the questions, but I just paused there for you. Okay, now we're going to talk about the projectile motion. Okay, so X is going to be going horizontally to the right. And by the way, the X they're talking about here starts there, and they're probably going to add X to this other number later. We'll see how that goes. So X is the horizontal to the right, and Y is the up and down thing. Now, Y equals 0 at the ground. That's the coordinate system we picked. And that means that, where are we initially in this projectile motion? Well, we're starting at, projectile motion starts at 114.7, because that's where we were up here. That's where we were on top of the building in one of those LSAs. And that's where the ball player hits the ball in the most recent thing. So that's good. Here it is. We have to figure out what is V0x in the x direction. Well, it's the same triangle, and this thing here was 22.36 is what V was in the x direction. And in the y direct, oh no, here we are. I'm sorry. This is Vx is that. So what we're doing here is this is going to be V0 times the cosine. And so this initial velocity in the x direction is going to be, and you see we had a component up here, and we figured, oh yeah, see, we figured out what was the velocity going along here. So in the x direction now, that's going to be velocity. Now, I got to tell you that, and I didn't write this solution. You might say, well, damn it, they started using x up here, and then they changed what x was. Yeah, and you know, but you can fight through that, but Linda would answer that question too. So you see this component of the velocity in the x direction over here, when you're in the projectile motion, is going to be this component. Then for the same reason I had it down here, it's the cosine of 35, and that gives me this as my velocity in the x direction. And the y is how much is it going up and down. So you see this is being split into up and down. And so this one is going to be V0 times 35, and that's what we get when we do this. And the acceleration in the x direction is 0, because the only acceleration in this problem, is when it is on, well, there's two accelerations. One is the acceleration when it's on the ramp, and the other acceleration that you get is when it is in free fall. So you see there's no acceleration in the x direction. Gravity only goes up and down. So this acceleration in that direction is 0. But here's the acceleration in the y direction. You see it's pulling down at 9.8. That's why the minus is, because it's pulling you down. That's meters per second squared. Okay. So, and now finally I got to the thing I was looking for before, because Linda's doing something here. I'm just, and Linda, that's fine. I'm just, but I'm.
Yeah, you can just X out of it.
Yeah. Okay. So anyway, here's what I was looking at before. You remember when I was saying x over 200 was that? Well, they're figuring out where was this. So this distance here, this distance along here, is 163.8 meters. Okay. Now this was all part of what your author here called the setup. But I think you should understand all of that stuff. And I am going to pause right here again. Now we're going to jump in and start solving stuff pretty quickly on this because we did a lot of work there. Does anybody have any additional questions on this part? Okay.
So I have a question on behalf of them. How do you know which equation you're supposed to use? So in the initial setup, then we're using the v sub x squared equals v sub naught squared plus 2 times the acceleration, so on. How do you know which one you're supposed to use?
Well, I will tell you. Now, you might not like the answer, and the students might not like the answer, but I think it's the correct answer. Whenever you see a problem like this again, you will know that's one of your equations that's there. And I also gave you a very big clue that you want to think about when you're solving a problem, and that is, gee, if they didn't tell me about time, I need to use an equation that doesn't have time in it. And this is, I think, almost the only equation that we have that does not have time in it. When you look across there, there is no time. And again, you're given this equation, so it's one of your equations. So I'm going to say, Linda, it's not easy. But you realize, oh, I don't have the time. There it is. And you have the experience of me doing this problem. You have the experience of doing other problems. You have the experience of maybe doing things in the low stakes assessment. I really don't know. I'd have to go back and look at the low stakes assessment. They might not tell you time, in which case you would use these. Now, Linda, I don't know if that made you happy, but that's the best answer I got. And Linda's actually very good. She was asking that question on your behalf. Anything else you want to say about that answer, Linda?
So I think that's a fine answer, but that leads to the other problem. Which variable means what? Because I feel like a lot of people are actually getting confused on what v sub x means. And if they knew what that was, then it would be easier to substitute into the equations and know which equation they're supposed to use.
Yeah, and that's true. And so and when we were going along, there are, I'm not going to say clues, but you're told that, okay? And here's when you're told that. I'm not saying this is easy. I mean, you have to read, you have to think. It's hard work. I know that, okay? So this is where they told you that. Motion along the incline, let plus x be directed up the incline. And then later on, they start using x for something different. But when they do, they tell you that for the projectile motion part, let plus x be horizontal to the right. Now, that's not easy. And by the way, you could have called it a different variable if you were working the problem, but I'm trying to show you the solutions. I'm trying to give you the solutions in a structured format here. So Linda, that's my answer for that. It's not easy. And so, you know, and Sydney, I do see you. I'm going to recognize you in just a minute, but I want to finish my response to Linda. Maybe I'm just going to stop talking. Linda, that's all I got. Do you want to say anything else, Linda, before I recognize Sydney on that?
So just generally speaking, v is velocity, a would be acceleration, x is position, y would be like vertical position, and if you have a sub-zero on any of these, then it means initial.
Yeah.
So I don't know if that clears anything up for you guys, but that's just a general rule of thumb.
Okay. Yes, Sydney.
So, like, when you're looking at a problem like this, like, in the actual question, like, what points out, like, what means what with, like, the variables and stuff, like, in the actual question? Like,
So, Professor Bradley, would you mind if we actually went back a slide and you can kind of label things in the problem?
I'm okay with that, Linda, but everybody should realize, and I'm not sure that, in fact, Linda, you know what I think is better to do, and you tell me if we can do this because I get confused when I'm in Blackboard Ultra and Zoom. I don't remember where I am. If you can throw up a whiteboard and not lose this, I would rather do that than go back a slide.
Either way, we're going to lose it.
Okay, so, all right, so we're screwed. So what I'm going to do is I'm going to draw it on this one. Okay, now, I'm not being mean. There is no crying in math. Okay, and there's a lot of ways for you to get help. Okay, I'm going to suggest that what you want to do, if these are, important sentiments, and I'm assuming that they are because you're writing all these things down here. Um, but those are that's my reaction to them. Okay, so it's ask a question or come in and get help or something like that. There should be no crying. That's kind of counterproductive. Actually, sometimes crying does make you feel better. I cried several times when my mother passed away. I'm better now, and so it can be therapeutic, but it didn't bring my mom back, and it doesn't help you do this. So maybe cry if that's therapeutic, but that's my reaction to this. I'm not being mean. Okay, and Linda, you want to say anything more about these comments that students offered here?
I mean, if you feel like crying, then that's exactly why you should come to tutoring. And at the very least, then we can figure out what we can do to make it better.
Okay, so I mean, and we're not being mean. In fact, Linda is the least mean person I know. Okay, and I try to be better all the time. So anyway, all right. So one of the questions was, yeah, and I think Sydney asked this question. It doesn't matter who asked it. To read the problem really carefully, and it would take me a long time to do this problem, and I bet it would take Linda a long time to do this problem from scratch. In fact, well, I don't know. Linda's pretty smart, so maybe she would do it quicker than me. But I would spend a long time doing this problem. And when I worked in industry, I'd spend a long time solving problems, things like that. And I do realize that your final exam is going to be an hour and 15 minutes. So I'm not going to ask you 100 problems like this. Okay. But I do say this is an opportunity for you to do this. Okay. So anyway, well, they told us that we were going along here 200. I remember that was in the problem. They told us that this was 35 degrees. They told us that, and by the way, if that's 200 degrees, or excuse me, 35 degrees, that means I can figure out what this is, and I can figure out what that is. They said you had an acceleration here. They told us what that is, and you were jumping off, and it was projectile motion. They're independent. So I think that's pretty much mostly what we've talked about here. So I figured out what this distance was, figured out what that distance was, and since I didn't know the time, I used this equation there. Okay. Now, Sydney, that's pretty much my answer to that. But the other part of my answer is, yeah, this is not the sports page. I read the sports page sometimes when I'm talking to my daughter because all I care about is did the Cubs win or lose or something like that, and I can listen to my daughter and be attentive to whatever she's telling me at the same time. I can't work a math problem and talk to my daughter at the same time. I either quit a math problem and I talk to my daughter, or I tell her, Beth, I'm busy right now. Can this wait? If it can wait, I finish my math problem, then I go talk to her. Okay, so that's where we are. Now we're ready to go into this. Sydney, that's probably the best answer I'm giving you inside this class right now. Okay? Yes, Sydney.
Okay, I just have one more question. Maybe not, though, I might be lying. But so okay, in the problem, like whenever there's a problem like this, do you always have to solve for every side of the triangle? Or
I'm
is
going
it
to say
just because
often you do. I mean, I knew we had to solve for both of these because we had to know where this started and we had to know, this distance along here. So we had to do all of that. Okay. And so, that was a good guess. But what I also do is read the problem carefully and I say, oh, what am I trying to find? And I work through it that way. Okay. So you are learning something as we're going through this one. Okay.
Thank you.
Okay. Now, this is something that came up in my office hours when we were talking about this. So this is something that some of you learned during my office hours. Some of you learned it watching the video, and some of you maybe have yet to learn it. If we have projectile motion that's going up and then it's going down, you see when it's still going up, the velocity is positive. When it's going down, the velocity is negative. So that means at this crest, the velocity is 0. So at the maximum height, the velocity in the y direction is 0. And again, we don't know the time, so we use this equation again. But we know everything else. You see, we're going to put 0 in for here because Vy is 0. And this is going to be V sub 0 y squared. And V sub 0 y, we know what that number is. We know what the acceleration is in the y direction. That's going to be the minus 9.8. And we know what y minus y0 is because y0 was at 114. It's going to hit the ground. So you see, I know what all of those things are. So I plug in the numbers, and I get that y minus y0 is 8.4 meters. Now that means the distance from going off the inclined plane, where you were at 114.7 meters. This up here is 8.4. You add them together, and you get 123. Now that was the question, Sydney, and I'm not picking on you, Sydney. Just I was talking to you, so your name is in my memory banks right now. And that's one of the questions they asked. The maximum height was at 123. Now the other question that they ask is, oh, where does it hit the ground? Okay, the horizontal range of the rocket. Okay, the time in the air can be calculated from the vertical component, y minus y0, which means this was 114.7 meters. Here's another one of our equations that we have. Now this one has time in it, and I know everything else. So you see, we want to know the time in the air. So we know that the initial velocity in the y direction was 12.83. We had that up here in the setup. And the acceleration is minus 9.8. So you have all this. I'm going to be substituting those things into this equation. And you end up with this. And that's a quadratic equation. And when does it hit the ground? It hits the ground when that is equal to 0. Now, Linda even has a song for the quadratic equation. Linda, do you want to sing that?
Oh, no. Oh,
So
no.
Linda is not going to perform that. The quadratic equation is something that you'll find, and it's and you solve for t. Here it is. And I'm not going to sing it, but I can recite it. This is minus b, plus or minus the square root of b squared, minus, and that's minus a minus, so it's plus 4ac, square root of all that, all over 2a. That's what t is. Now, you remember from your math that you can have two answers. It could be 6.32 seconds, or it can be 0. Okay, or wait, where's the quadratic? Oh, the other one is negative, and time can't be negative. There you go. Okay, and here this was a plus or minus. Okay, so anyway, the answer is 6.32. Now, Sydney, going back to the discussion that you and I were having, would it take you a while to solve the quadratic formula? Yeah, probably so. It would take Linda a while and me a while too. We do let you have calculators, and that's what you're doing. And so you see, it's not trivial to do that. But I hope you see where that's coming from. Okay, now we know a value for t. And now what we can do is we can use this formula, which is right here. This tells you where are we in the x direction. And you see that the x direction I don't know if that was a question or being answered, and Linda will probably care for whether that's being answered or whatever. Okay, but this is what t is. That's how long you are. The time in the air, we're going from this spot down, and then also that. So what we do is we substitute this in, and we know, or we're finding the range, excuse me. That's how long it's in the air, so we substitute into this equation, and we substitute the value for t and v sub 0 in the x direction, and so on and so forth. We get this number, and so x was that number plus this number, because remember we had this distance here, we had this distance from part A. So the answer is the horizontal range of the rocket is 280 meters. Now, you may need to think about this for a while because, you know, it does require study, it does require thought. Okay, Linda, let's go to the next slide.
Okay.
And here are some of those MCAT type problems dealing with projectile motion. Now, these are different. They're multiple choice. This talks about this, but Linda, go to the next slide. Here are the solutions. So those are there. If you say, oh, I would like some more problems to practice on, here's some more you can practice on. I'm not going to spend more time on this because I'm going to talk about a little bit more into the chapter that we've been covering, and maybe I'll do a problem or two there. Now, what's going to happen is that was a pretty complicated problem that we just did. There are easier problems that are there. Are we going to ask you an easier problem on an exam, on lower stakes assessment? Maybe not, because I want you to spend time on that. I'm giving you a week to do it. Okay, so Linda, let's advance the slide then, please.
Yeah, we still have somebody crying.
All right, here's what I'm going to ask, okay? And you don't have to, you know, show up with tears in your face or anything like that. And I'm not going to ask you that. And you can always leave your video off when you come to my office hours. I have office hours at 7:30 tonight, 7:30 to 8:30. So if you're that upset, I don't want you to be that upset. So I'm going to encourage you and anybody else who wants to come to my office hours tonight at 7:30, and you know, I'll you know, talk with you. I'll try to answer questions. Probably one of my goals is going to be to make you feel better, because I think you'll be all right. Okay, many students are not used to the level of math that we're doing. Many students, you know, it's a challenge. There's a lot to remember and things like that. It's important you don't get yourself overwhelmed. Linda, most students end up just fine in this course, don't they? Linda and I have done this a lot.
Absolutely.
Okay, so that's one of the things I'm going to tell you. I mean, I'm telling you all this right now. In fact, I told you that earlier in the period, but you know, I can tell you that privately too, and I can talk about some things that if there's things you don't understand as well. Okay, now this is a little bit of a summary of a video. You really should watch the video. Force is a vector quantity. Okay, and so, and when it comes in newtons. So you see, if you got a force, you can break it into components. So it's like that. Okay, and we actually solve vector problems like that. But that's what a force is. I talk a lot more about force in the video, and I encourage you to watch those videos if you haven't watched them. I'm going to go ahead, next slide, please. I was just reminding this to you so you could do it. I talked about Newton's first and second law. Newton's first law states that when no force acts on an object, or when the vector sum of all the forces acting on it is 0, the object is said to be in equilibrium. That means it moves with constant velocity. The velocity does not change, because if it did, there would be an acceleration. Okay, so force is related to acceleration. And if it's in equilibrium, the velocity doesn't change. If the acceleration is 0, it doesn't change. These are called inertial reference frames, and I talk more about that in the video too. Go to the next slide, Linda, please. Those are good videos, I think, actually. I think they're very good videos. And Newton's second law says, you remember this from high school, some of you do, force is a vector, so the net force, you might say, well, in high school we just said F equals ma. Well, maybe you did, but the net force is the mass times the acceleration. And in the x direction, the net force in the x direction is the mass times the acceleration in the x direction. And the net force in the y direction is the mass times the acceleration in the y direction. So here it goes again. An object's acceleration depends on its mass and on the net force acting on it. The net force is you add all these forces together and figure out what it is. Linda, another slide, please. This is something that was alluded to in the videos that I provided for you. And again, I would really encourage you to watch those videos and watch them with pencil and paper in hand. It's not like watching, let's see, what kind of videos do I sometimes, actually, I don't watch these kind of videos, but I understand that Ellen and her wife watch cat videos on YouTube all the time. I don't watch cat videos, but the videos that I put on YouTube, you have to watch with a pencil and paper. I don't know if Ellen and her name, her name's not Priscilla, what is it?
It's Portia de la Rosa or Rosa.
Okay, thank you. Because I wasn't remembering that. And when I think of Porsche, I don't think of someone, I think of a car. But anyway, you're right. Thank you. Okay, so anyway, there's a difference between mass and weight. And the weight of an object is a gravitational force exerted on it by the Earth, or whatever object exerts the gravitational force. Weight is a force, and therefore weight is a vector quantity. But the magnitude of the weight of an object at any location is equal to the product of the mass of the object, and the acceleration due to gravity. So that is the magnitude of the weight. And so the weight is a vector, and it's going to be the mass, and it's going to be going down towards the center of the Earth if you're on the Earth. Now, an object's weight depends on its mass and on the acceleration due to gravity at its location. And that's even true if you jump out of, if I were to go to the moon, my weight on the moon would be different because the gravity on the moon is different. My mass would be the same when I was on the moon. The mass is how much of Jim Bradley is there. A mass comes in, we know this, comes in kilograms. Acceleration comes in, this is mass. I should write that out because I've got another one. So mass comes in kilograms. Acceleration comes in meters per second squared. But you see, if I multiply mass, which is kilograms, times meters per second squared, I get kilogram meter per second squared. Okay. You might say, well, Jim, I thought we called that a Newton. And yes, we do. So you see, a Newton is a kilogram meter per second squared, because you see this is a force, so that's going to be a kilogram, and that's meters per second squared. It comes in newtons, but whenever you're doing dimensional analysis and you're talking about newtons, this happens. You might say, well, gee, are we going to have to do dimensional analysis? Well, you betcha, because there's all kinds of dimensional analysis in ultrasound. Okay, Linda, go to the next slide, please. Now, I think you're going to be really pleased. This problem is way easier than what we did before. And I know what time it is, and we're going to finish this problem before the period is over. And now we've moved along. Maybe we didn't get quite as far as I had hoped, but there's plenty of leftovers for you to deal with, and and also the things that I summarized there were things that were covered in the videos that the VCM folks as well as the net folks are supposed to look at. Now, I realize you guys are all busy too. I do understand that, but this is a 3-hour course. I'm teaching the best 3-hour course I know how to teach, so we'll have that. Somebody said, yay. I don't know if that's because the period's almost over or what. But anyway, here we go. This problem is easier, and maybe that's what they were saying. Okay. So anyway, advertisement claims that a particular automobile can stop on a dime. Okay. Now it's kind of BS, but the question that's being asked is, what net force would actually be necessary to stop an automobile with this? This is mass, that's kilograms, traveling at 45 kilometers per hour. That's a velocity, isn't it? In a distance equal to the diameter of a dime, which is 1.8 centimeters. Now you see you got all kinds of units flying about here and everything else. One of your big formulas is F. By the way, that's net force is equal to mass times the acceleration. Now we've got other things. We have velocity is equal to distance over time. These are formulas that are in your grace notes, and we've covered them. And yes, you have to use these to solve problems. There's a formula. There's a formula. I don't know what else I want to do. Distance is velocity times the time, and we're stopping that much. Okay. So, and we've got an initial velocity, which is this. But you want to stop. That means you go take that to 0. Okay, Linda, let's go and look at the solution. Here it is. So we're going to calculate A in the x direction. And by the way, this car is just going along a flat road, so we just call that x. So we want to know what acceleration. That was the question that was asked. You see, what net force? Okay, so we need to know the acceleration. Then, to find the force, we'll say, oh, net force is equal to ma, because net force is ma. So, and we also know that this is the direction of the initial motion of the automobile, and we just picked that because there's something happening here. No one told us time, did they, Linda?
Nope, no time.
That means no time left for you. Okay, so anyway, I said I wasn't going to sing. So anyway, there was no time. That motivates me to use this equation. I know everything else. And the thing I don't know is this. I plug in all the numbers, and v sub x was 0, because at the end of this problem, you want to be stopped. You want that to be 0. So you get A is this. Okay. And there's a bunch of people who are leaving the session, and I hope maybe they're going to care for things so they can come to my office hours. I don't know, but they're going to miss the punchline on this problem. So anyway, F, so the acceleration is equal to minus F over m. And so we equate those two expressions, okay? So we say that, that we have two expressions for A. We have this one, and we have this one. So when we set the two equal, what we're able to do is, what will happen is everything is a number. We just plug those in. The force is going to be equal to, there's 8 kilograms. There's meters squared over seconds squared, and this was, and we changed meters to centimeters, and we end up with this. Because if you work through this, this is kilogram. Meter squared cancels with meters, so it's kilogram meter per second squared. So you see the units are in newtons. Okay. 7:15, I have office at 7:30, but and then we're going to poll. And the poll is, and actually I don't want to because a whole bunch of people left. Okay, so I won't, I won't bother with that. Okay, time is precious. Each day must count. Do the math. It'll make you strong. Maybe I'll see some of you at 7:30. You're certainly welcome at 7:30. Linda, when's your next opportunity for students to come and visit you?
That would be Monday at 11 a.m. in the Blackboard Collaborate daily drop-in.
Okay, and I'm going to be asking Tom Topple to tell you the times too. Okay, Take care, everybody. Good night.
Have a nice night.
Night.
Hey, Linda.